Okay, so hello and welcome back. So in this video we want to do a couple of examples after we have gone through basically in the previous video we talked about the limits of rational functions and polynomial functions, and so here what we need to do is we will just do a couple of examples. So for example, let's say that you have the limit of x cubed minus x squared plus 1 as x tends to 1. So based on the algebra of limits, we said that if you have had the limit of a polynomial function, which is basically this is of course a polynomial function of degree 3, but of course x is not there. The first power of x is not there, which doesn't really make any, it's not really a problem. But nonetheless, it's a polynomial of degree 3, and using the rule that we found for the polynomials, we said that basically if f of x is a polynomial of degree n, then the limit of f of x as x tends to a is equal to f of a. So based on this, then you can say that if you think of this as f of x, then f of a would be the value of this function at x is equal to 1, which is basically 1 raised to the power 3 minus 1 raised to the power 2 plus 1, which is equal to 1 minus 1 plus 1, which is equal to 1. Or let's say you have the limit of x times x plus 1, the limit of x times x plus 1 as x tends to 3. This is again a polynomial function, and so you can calculate the value of function at that input, which is equal to 3 times 3 plus 1, which is equal to 3 times 4, which is equal to 12. Or let's suppose that you have, for example, some limit, like for example the limit of 1 plus x squared plus all the way up to x raised to the power 10. When x tends to negative 1. So as you can see, what you will have here is basically positive 1, and over here you have negative 1, over here you have positive 1, and then x cubed would be negative 1, plus all the way up to x raised to the power 10, which would be positive 1. Now, in order to be able to calculate the sum of all of these numbers, you have 1 negative 1, 1 negative 1, and so on and so forth, ending in positive 1. And you know that okay, so in order to basically there are two ways to calculate this. First of all, you can rewrite you can rewrite this all the terms of the polynomial and then add them together one by one, basically -1 plus 1, -1 plus 1, and so on and so forth. But you see this part over here, from x raised to the power 1 all the way up to x raised to the power 10, you have 10 terms over here. And so 10 terms, it starts with a -1. It starts with a -1 and then goes all the way up to +1. And of course it changes periodically, meaning that you have -1, +1, -1, +1, and so on and so forth. That means that every 2 terms you will get a 0. So you have 5 times 2 terms, which is 10 terms. So then ultimately you will get a 0 plus 0 plus 0, 5 zeros together. So 0 plus 0 plus 0 plus 0 plus 0. So that would be 5 zeros together. So this whole thing would be just a 0. And then you will end up with a 1. Now, example number 2 here is you want to find the limits of, for example, the limit of x squared plus 1 over x plus 100. As x tends to 1. So this is a rational function, and we said that basically if you have some f of x as a rational function, and if f of x is equal to g of x by h of x, where h of x is not equal to 0, then the limit of f of x as x tends to a is equal to the limit of g of x as x tends to a over the limit of h of x as x tends to a. And well, these are both polynomials, so then you could write this as g of a over h of a. And then we had all of those two basically cases where basically we said that if g of a is equal to 0, then there are two cases basically, if g of a is equal to 0 or if g of a is not equal to 0. If g of a is equal to 0, that's a different story. If g of a is not equal to 0, then you would have some number. You would have some non-zero number divided by 0, which in this case the limit does not exist. In this case, what we did was that we had to basically rewrite the numerator and the denominator in terms of, for example, in terms of x minus a. Basically we had to rewrite the numerator and denominator from here in terms of x minus a raised to the power k, for example, times, for example, g1 of x over x minus a raised to the power l times h1 of x. And in one case we got, basically there would be two cases. If k is greater than if k was greater than l, then basically the limit would be, the limit is equal to 0. Otherwise, if k is less than l, then basically the limit does not exist. The limit does not exist. So now using this example, I'll show you what these steps actually mean in terms of an actual rational function. So let's say that you have this rational function over here. So then we said that this is going to be g of basically the value of this function, the numerator as a function at x is equal to a, over the value of this function in the denominator at x is equal to 1. So that's going to be basically 1 plus 1 over 1 plus 100, which is equal to 2 over 101, which is equal to 2 over 101, which is the value of the limit of this rational function as x tends to 1. That is the limit of the value of the limit of the function. So here we had no such problems. Okay, so the next question that we have here is number 2. This is example number 2, and this example has basically 5 parts. So part 2 of this example is you want to find the limit of x cubed minus 4x squared plus 4x over x squared minus 4 as x tends to 2, I suppose. So you see over here what happens is that, and you want to find the limit of this whole rational function. So you see what happens is that here your limit, basically you want to find the limit of this function as x tends to 2. So if you evaluate this rational function at this prescribed value, as explained in the book, they use this kind of language. They say evaluate the function at the prescribed value, like you've gone to a doctor or so. So if you evaluate the function at that value, you will get 2 cubed is equal to 8, and then 2 squared is equal to 4 times negative 4 is equal to negative 16, and then 4 times 2 is equal to 8 over 4 minus 4. So this is 16 minus 16, which is equal to 0, and 4 minus 4 is equal to 0. So we got to that problem where basically where you get to the form 0 by 0. And this is something interesting and useful that happens because, and the reason is, and the reason why I'm saying this is actually very, very important. I'll tell you why I'm saying this. Okay, so this is an interesting case in finding the limit of a function, basically the case 0 by 0, and the reason why I'm saying this is that basically when we had that distance function, the position function with respect to time, we got basically some function like this. We got some function like this. Okay, and this function was basically this was position, or S, distance. Distance meaning distance from some point. For example, we talked about that edge of the cliff, and then the distance of that piece of stone, for example, from the edge of the cliff at any point in time was, for example, some distance, and you can call that the position. In calculus, they usually call that the position function. I mean, technically they call it the position function, and they denote this by P usually, standing for position. So that was basically the position function, and position basically comes, I suppose, from this very popular example of a car basically moving down a straight road or something like that. Suppose that your car is over here, and for example, this position is 0 kilometers or 0 miles or something like that, and then after some time the position of the car has changed with respect to this time, so then they call this the position function. Otherwise, it's basically the same example that we talked about, and we call the distance over there. It's basically the same thing. Now over here we said that basically we picked some point over here on the graph of the function, and we call this, for example, T1, and at T1 the position of the stone was at this position, for example, S1, and then at, for example, T2, sometime after T1, the position of the stone was at S2. And then we said that the average velocity of the stone was basically the slope of this line, which was practically the covered distance divided by the time taken during that trip. And then what we did basically was that we got closer to this point, so as to get a better idea of the velocity of the object at this point exactly. And then that basically meant that, for example, this was, for example, T3, and this was, for example, S3, and then we calculated the slope of this line, and then we did the same thing, for example, for a point closer to that point, and then we calculated the slope of this line, and so on and so forth, until we got to a point very, very, very infinitesimally close to T1. And of course, if you want your average velocity to be exactly instantaneous velocity exactly at this moment T1, then the 2 points have to be practically exactly one and the same point, meaning that you have to cover zero distance and of course zero distance in no time, in zero time, and that would be 0 by 0. So now logically, when there is zero distance in zero time, there was no trip, and there was no velocity, and there was no average velocity, and there was no motion, and there was no instantaneous velocity. That's what logic tells you. But reality is different. Reality is that when an object is moving, when there is motion, or when an object is moving, of course the object, we know that the object is moving. That's something that we already know. We don't need, for example, we don't need mathematics to tell us that this object is moving. For example, if you shoot an arrow from this point towards another person over here, we know that we know that the arrow is, if the arrow is shot basically exactly at this person, then invariably the arrow is going to hit this person, of course, provided that you have a proper distance between the arrow and the person, and the proper basically initial force given to the arrow, and all of those basically considerations. But ultimately, if you shoot an arrow properly at the person, the arrow is going to hit the person. That's what we know. We don't need really mathematics or physics to tell us that. But then when you want, and this was the Zeno's paradox, that basically logically he argued that, yeah, I know that the arrow has been shot and is moving towards me, but if I think of this arrow moving in time, basically in one instant of time, the arrow is not moving. So then the arrow is not going to reach me at all, which is not the case really. The arrow is going to reach the person ultimately. So then logic basically tells you that when there is zero distance over zero time, there is no motion, and then the whole story is basically ended over there. There is no velocity and there is no instantaneous velocity, and that would be the end of the story as logic would anticipate. But well, that's not the case. And basically what limit does is that it resolves this problem of dividing 0 by 0, and it will actually give you an answer. Now, I don't really know, I mean, to be completely frank with you, because it needs a very, very complete and good understanding of the concept of limit. I don't really know how it does it. Except that, for example, you factorize some factor out of your numerator and denominator, and then you cancel them out, and then you will get some answer in the limit. Which I will have to think about a little bit and see how that actually works and what that actually means in terms of the algebra, in terms of the algebra of the functions, and that the whole story there. But anyway, basically the limit is actually solving that problem for you, the problem of 0 by 0, and is giving you, and is actually giving you the instantaneous velocity of that object moving at that exact point in time. For example, assuming that this expression up here is your distance covered, and this expression over here represents, for example, the time taken for the object to cover that distance, which is the power of basically the concept of limits. And that's basically why I call this the art of the limit. So that's basically that. Now, apart from the concept, now if you want to calculate this limit over here, what you need to do, basically we said that we need to take out basically the factor that is creating this problem of 0 by 0. And so, for example, in this particular case, what you can do is that you can write basically, for example, if you have x cubed plus minus 4x squared plus 4x, what you can do with that, you can write it as, you can take an x out and write it as x times x squared, for example, minus 4x plus 4. And then again, you can factorize this second degree polynomial or quadratic expression or equation, if you will, and that will give you basically 4 times 4 would be 2 times 2. So I take it as -2, and -2 times -2 is +4. -2 plus -2 is equal to -4. So I can write this as then x squared minus 4x plus 4. I can write it as x squared minus 2x plus 4. And then that would be x times x minus 2 times x minus 2. And that would be x minus 2 times x minus 2, which would be x minus 2 whole squared. So then you can write this whole basically numerator as x times x minus 2 whole squared. And so I can write this limit then as the limit of x tends to 2 of x times x minus 2 whole squared, and this is basically x minus 2 times x plus 2, x minus 2 times x plus 2. And then you can, and since, if you remember basically now you can please go back in that definition, basically in that procedure that we talked about, the limit in that mysterious basically procedure that we talked about, that there was k and there was l, and we said that k is greater than l and l is less than, l is greater than k, and so on, and so the whole thing over there. We said that somewhere in that explanation, I said that as x is not equal to a. Somewhere over there I said this part. So what that means is that, now of course, normally if I had a function over here, for example, x over x minus 2 whole squared over x minus 2 times x plus 2, I couldn't just simply write this as x times x minus 2 whole squared times x minus 2 times x plus 2, and then I couldn't just say, okay, so this is basically, since I have these common factors in the numerator and denominator, I will simply cancel this out with this one and write this as x minus 2 raised to the first power. It's not possible, because the way that this function has been written, it's been written in such a way that x cannot be equal to 2, cannot be equal to 2. If you set x is equal to 2 in this function, what happens is that you will get 2 minus 2, 0, and the whole function doesn't work anymore, because you're dividing by 0. So here x cannot be equal to 2. Now here x is not equal to 2, x is tending to 2, getting very close to 2. And so you can write this expression as the limit of basically x times x minus 2 over x plus 2, cancel these out, as x tends to 2, as x is not equal to 2. Okay, that's basically the meaning of that part over that we said. You will understand all of that explanation piece by piece as we go through these examples. Otherwise, if you want to try to understand that explanation, you will never understand it really. So now what happens is that now I can substitute this value x4 in the numerator and denominator and calculate my limit. I can write this as basically 2 times 2 minus 2 over 2 plus 2. And you see that the denominator is not 0 anymore. So this is equal to 0 over 4, which is equal to 0. So which means that basically the limit of the function is equal to 0, and what 0 is, what that means that it's defined. Now what that means in terms of, for example, a practical, an actual function, I will show you what this means later when we get into derivatives. We will define derivatives, and then over there I'll show you what it means what it means when the limit of the function becomes 0. For example, at some point I'll show you what that means. But for now, please bear with me until we get there. Okay, so now part number 3 of this question is, so let's go over here and E31. Part number 3 of this question is limit of, we want to calculate the limit of x squared minus 4 over x cubed minus 4x squared plus 4x when x tends to 2. So basically, if you evaluate this function at x is equal to 2, what you will get is basically 2 squared is equal to 4 minus 4, 2 cubed is equal to 8, minus 4 times 4 plus 8, which is equal to 0 over this is 16 minus 16 is equal to 0. So you get to the same form, 0 by 0. So what you can do is that you can write this limit as the limit of x tends to 2 of x minus 2 times x plus 2, and then you multiply that by, for example, you divide that by, for example, x times x squared minus 4x plus 4, and this is x minus 2 whole squared. So that's x times x minus 2 whole squared. And over here, as you can see, since x is not equal to 2, then you can basically cancel these out with this power, and you get x plus 2 over x times x minus 2, and you will get basically 4 over basically 0, which means that basically the limit does not exist, which is not defined. Now what we did over here, basically this was basically the case where we said that, for example, you take the limit of f of x as x tends to a, and that was equal to, as a rational function, the limit of g of x over h of x as x tends to a over which is basically, and since we got 0 by 0, then you write the limit of basically x tends to a of basically x minus a raised to the power k, for example, times g1 of x and over here your h of x, you can write x minus a raised to the power L, for example, times h1 of x and that's exactly what we did over here. You see, basically the numerator, we were supposed to write it as x minus a raised to the power k times g1 of x. So x minus a in this case is, for example, x minus 2. And over here the power is 1, and over here the power is 2. And then, for example, g1 of x in this case is basically this function, this polynomial function, which is x plus 2. And h1 of x in this case is, for example, x. So this way now you can understand what we said, what we meant when we talked about all of those limits and all of those steps and so on and so forth. And then we said that if k is less than L, if k is less than L, which is basically the case over here, you see k over here is 1, L is equal to 2, k is less than L. If you remember, we said that basically the limit is not defined in that case because you will get a 0 in the denominator, because then you would write, if k is equal to, if k is less than L, then you would write this as the limit of basically x minus a, assuming that k is less than L, then L is greater than k. So x minus a raised to the power L minus k times h1 of x, and the numerator becomes g1 of x. And so since this becomes 0, so since this in the limit becomes 0, x raised to a, x tends to a, since this becomes 0, then of course you can say that the limit does not exist. So this is the meaning of what we said over here in this example, and based on the example now you can understand it. That's basically that. Let's say you have question number 4 is basically the limit of x cubed minus 2 times x squared over x squared minus 5x plus 6 as x tends to 2, for example. So first you can always evaluate your function at the value of x, or value of a basically. So that would be equal to basically 2 cubed is equal to 8 minus 2 times 2 squared, which is equal to 4. And then this would be 4 minus 5 times 2 is equal to 10 plus 6, which is equal to 8 minus 8. And over here you have 10 minus negative 10 plus 10 is equal to 0. So that's 8 minus is equal to 0 by 0, which is just at this point is just 0 by 0. So then you can write basically x cubed minus 2 times x squared. You can write it as x squared times x minus 2. X squared times, this is x cubed minus 2x squared. And x squared minus 5x plus 6 is equal to basically 3 and 2. So I can write this as x squared negative 2x negative 3x plus 6, which is the same thing as x times x minus 2, negative 3 times x minus 2, which is the same thing as x minus 3 times x minus 2. So this is your denominator, and this is your numerator. So I can write this limit as the limit of x tends to 2 of x squared times x minus 2 over x minus 3 times x minus 2. And so what you have here, since x is not equal to 2, you can cancel these two out, and as you can see here, you get no problems, because basically we said that basically the numerator, the polynomial in the numerator, we wrote it as, we called it h of g of x. The numerator in the denominator, we called it h of x. And we said that we would write this as x minus a raised to the power k times g1 of x, and then we write x minus a raised to the power l times h1 of x. And as you can see over here, x minus a in this case is x minus 2. And you can see that the power here is 1, the power here is 1. So that means that k is equal to l. So this will cancel out with this one, and then you have g1 of x and h1 of x, and then in the limit you will get a number. So that's basically that. So we did not discuss this part directly in that process, but it's actually a part of that process. When k is equal to l, then you will get a value for the limit, which means that now, since x is not equal to 2, I can simplify these two together, and this becomes the limit of x squared as x tends to 2, and this the denominator becomes the limit of x minus 3 as x tends to 2. And so what that means is that then the limit of x squared as x tends to 2 is equal to, well, 2 squared is equal to 4. That is equal to 4. And the limit of x minus 3 as x tends to 2 is equal to negative 1. Is equal to negative 1. So that is negative 4. So that was part number 4 of these questions. Now part number 5 is the limit of x tends to 1 of x minus 2 over x squared minus x minus 1 over x cubed minus 3x squared plus 2x, the limit of this whole expression as x tends to 1. So what you need to do is, let me see how they have solved this problem. Okay, so now basically your function is in this form, basically some rational function minus some other rational function. So what we can do is that we can rewrite this function as just one rational function. So and for that basically I would need to take the LCM of these two denominators. So x squared, x squared minus x, I can write it as x times x minus 1. And x cubed minus 3 times x squared plus 2x is the same thing as x times x squared minus 3 times x plus 2. Now this part over here, I can write it as x squared minus 3x plus 2. 2 and 1, so I can write this as x squared minus 2x minus x plus 2, which is equal to basically x times x minus 2 minus 1 times x minus 2 minus x plus 2, so that is x minus 1 times x minus 2. So I can write this as x times x minus 1 times x minus 2. And so I can rewrite this basically this as this expression as the limit of x tends to 1 of basically x minus 2, I'm sorry, not this way, x minus 2 over x times x minus 1, x times x minus 1, minus basically 1 over x times x minus 1 times x minus 2. And what that means is that then you can take the LCM as x times x minus 1 times x minus 2. You can write this as the limit of basically x times x minus 1 times x minus 2, and then that would be, this would be basically x minus 2 whole squared minus 1 minus 1. And so that is basically my as x tends to 1, and that is my the limit as a rational function. Now if I evaluate this expression as at x is equal to 1, what I will get is basically 1 minus 2 whole squared minus 1 over 1 times 0 times, and then 1 minus 2 is negative 1, and that is equal to negative 1 squared is positive 1 minus 1 over 0, which is equal to 0 over 0. So you would get 0 over 0 if you evaluate this expression at x is equal to 1. Now let's see what the limit of the same expression is as x tends to 1. So you saw that the value of this expression or this function as x, if x is equal to 1, then it's going to be 0 by 0, which is something that I cannot do anything with. Now let's see what the limit of this expression is as x tends to 1. So in order to do that, what I need to do is that basically x minus 2 whole squared minus 1, I write it as x squared minus 2 times 2 minus 4x plus 4 minus 1, which is equal to x squared minus 4x, 4 minus 1 is equal to 3. And then I can write this as basically 3 is the same thing as negative 1 and negative 3. So I write this as x squared negative 3x negative x plus 3. And that's the same thing as x times x minus 3 minus 1 times x minus 3, which is the same thing as x minus 1 times x minus 3. So I can write this as the limit of x minus 1 times x minus 3 over x times x minus 1 times x minus 2. And that is of course the limit of that. That is of course the limit of x tends to 1 of this whole expression. And since x is not equal to 1, only tending to 1, I can simplify these two expressions together and now take the limit, meaning that now I can evaluate the expression at x is equal to 1, which is equal to basically 1 minus 3 over 1 times 1 minus 2, which is equal to negative 2, and this is negative 1, so this is equal to positive 2. So this is positive 2. And of course here again we can basically simplify this expression by cancelling out these two factors of x minus 1 over here. And the reason why you can do that is that because I know that x is not equal to 1, at least relative to what I'm doing over here, I know that x is not equal to 1. In very simple words, what this basically means is that suppose let me write a function, for example. I saw this once in Khan Academy, and it's actually the best way to explain this concept. That's why basically it's not why you have to be careful when you're simplifying these things in a function. Now suppose that, for example, having the same type of example, suppose I write f of x is equal to 1. This is a constant function, meaning that if I draw the graph of this function, it's going to be some line like this, which is a constant line. This is f of x is equal to 1. Now you can see that this line for this function, wherever you go from negative infinity all the way up to positive infinity, the output of this function is positive 1, positive 1, positive 1, all the way from negative infinity to positive infinity. Meaning that this function is defined for all real numbers, no exception. Now suppose that I write another function, f of x is equal to x minus 1 over x minus 1. Now of course you would say that, or not of course, but you might actually say that, so I would just simply simplify these two together and I write this as f of x is equal to 1. But that would not be the same thing, because you see this function over here, the domain of this function is such that basically x minus 1, which is the denominator, is not supposed to be equal to 0. And so that means that x is not equal to positive 1. And so if I want to draw the graph of this function, the output of this function is going to be 1 except for x is equal to 1, meaning that I will get some function like this, and this is the graph of the function. This is the x-axis and this is the y-axis. Now at x is equal to 1, the function is not defined. At x is equal to 1, the function is not defined. So you will get this hollow circle over here, meaning that at this point the function is not defined, and except for this point, every other input for the at every other input, the output of the function is equal to 1, 1, 1, 1, and so on and so forth. So you can write this function as, basically you can write this function as f of x is equal to 1 and x is not equal to 1. You can write it this way, or you can write it as f of x is equal to x minus 1 over x minus 1. Both ways you can write that, and that means the same thing. But of course you cannot just simplify these two together and get a 1 over here. That would not be right, because then you would miss this point. And whatever this function represents, suppose that this function represents, for example, some phenomenon that you've got somewhere in physics, and in that, based on that situation, at x is equal to 1, then you're not supposed to have any output relative to that experiment, for example, or relative to that phenomenon. So of course your function has to convey that sort of information that you've gotten in your experiment. And so for the same reason, you write your function this way, meaning that whoever is supposed to be using this paper or this basically function or whatever, they need to know that they're not supposed to use this function at x is equal to 1, because the function is not really giving out anything meaningful at x is equal to 1. And that's basically why I cannot just simplify these two together, because the person who wrote this function, of course this is just a hypothetical situation, right? This doesn't convey any real world information or anything like that, just a hypothetical situation. But if it was not a hypothetical situation, the one that would written this would have meant something by writing this factor of x minus 1 in the denominator. What they meant by this is that basically what they would have meant by this is that, hey, be careful, x is not supposed to be equal to 0, x is not supposed to be equal to 1, and x is not supposed to be equal to 2. Other than that, you can enter any value of x into this function and get basically the output that you're looking for. So that's basically the whole story here. Now there is another theorem here that we will go through in just a few moments, or basically in the next video. So I'll see you in the next video, and thank you.